Welcome back to the programming language series where we're going to build a statically typed and JIT compiled language all using Python and LLVM Lite. Last time we got the Lexer situated for our arithmetic language. So today we're going to get the parser situated for our language, and we're going to be using a technique called Pratt parsing. I'll let you guys read more down in the description below on Pratt parsing, but we will get right into building this out. So the first thing we're going to do is create a tests file. So we're going to call that parser.lime. And we're just going to put 5 plus 5 in here for right now. So from here, after we have this file created, we can get out of that. We won't need it for a little bit. We'll go ahead in the main.py file, change that to parser.lime. And then we will create our parser.py file and get started. Few imports that we're going to need is our Lexer. So from Lexer, import Lexer. From our token, we're going to need our token class and our token type class. Oh, from. Yep. There we go. And then another typing import. This is optional, of course, but I like it for the IntelliSense. We're going to import callable, which is pretty much just like a function type. And then we're also creating another enum. So from enum, import, if I can spell, enum and auto. And that's all for the imports right now. We're going to set up our precedence types. The Pratt parser is an operator precedence parser. So we need to set up kind of how our precedences are mapped and what levels, which one's the lowest and the highest. So for that type, this is going to be a enum precedence type. We'll inherit from that enum class. First one we're going to implement is p lowest, which is this is the lowest precedence. Absolutely the least priority, pretty much. We're going to go to p equals, and we're going to use that auto function that we imported. All this does is it just takes the next, it replaces it with the next appropriate value in this enum class. Since we're starting with a 0, the auto function is just going to have it a 1, and then p less greater equals auto, that's going to resolve to 2. And we're using this auto function that way later on when we add different precedence types or levels, we don't have to actually change everything. So we don't have to change this to 2 if we add 1 here. So this auto function is just going to help out later. Now there's a few more. I'm going to save some time from having to type that out. But we have p sum, product, exponent, prefix, call, and index. Now this is every precedence that we should need throughout this series. There will be more, of course, if we have some requested features, but this should do for a while. Next thing is going to be our precedence mapping. And this is just going to be a big dictionary. Keys the token type, and we're going to call a, not an int, but precedence type as the value. So the first one we're going to implement is token type dot plus. This is the plus symbol, the plus token, and that is of course going to map to our p sum value or precedence type. And we're going to implement every other operator that we have. So we have minus, slash, asterisk, modulus, and pow. We'll have a lot more in this class, or this dictionary, but for right now this is all that we need. This is everything we have implemented. So we'll go down and we'll start our parser class. So we'll add a class parser. We'll add a constructor init method. The only thing that this constructor is going to take in is an instance of our Lexer, and we'll set a variable self.lexer, type Lexer equals Lexer, or not Lex, the actual variable. We're going to have an error list. So for right now, all we're going to care about error handling is just having a list of strings. So self.errors is a list of strings, and we'll just print out the errors as we generate them. We'll have a more robust error system later down the line, but for now this will do. We need two variables, self_current token, so whatever token the parser is currently on, and then we'll have a peak token, which is whatever token is next, what the parser is going to take on next. Then we'll have two dictionaries. We'll have a prefix parse functions. This will be a dict of token type. Valuable is going to be a function to call based on the token. We'll keep that. Prefix functions basically are going to handle like -1. This little negative symbol is a prefix to 1. We're going to have infix parse functions. That'll be a token type and a callable for the value. And infix functions are going to handle like 5 + 5. So the operators inside are in the middle of two other nodes, so 5 and 5. The last thing we're going to set up, we don't have this function yet, but this is what we're grabbing next, is our next token function, very similar to our lexer. And this will actually call our lexer as well. Moving into our next token function, I'm going to do some region blocks just to kind of help. This file will be very large in the future, so it's always going to be good to have these region blocks to segment out the code. And all that does is you can collapse everything in this region block really easily, and this is its title. Moving into the def, next token, have self, and we will grab none for the return type. So we're going to take the self.current token, we're going to set that to our peak token, so the next token, and then we're going to basically increment this peak token to be whatever the next token is from the lexer. And that is all for the next token function. What we're going to do is go ahead and build out all of these helper functions just to avoid us having to go back and forth throughout the code to recreate helper functions. And I feel like that would be a little more confusing than just getting them out of the way right now and explaining them. So the next function we're going to implement is our peak token. Peak token is. That's going to have a self and a token type, TT token type. That's going to return a Boolean. This basically just checks our peak token that we have saved in the parser class and checks its type and see if it is equal to the one that was passed in. So self.peakToken.type equals TT. Next one is going to be __ expect peak self TT and token type. This function is going to basically expect, we're going to check because we're expecting the peak token to be of a certain type, and if it's not, we're going to throw an error. So if self dot __ peak token is, if the peak token is that token type, we're going to increment the tokens and we're going to return true. Else, we're going to throw another function we'll create in a second, peak error, with the token type, and we'll return false. All this peak error function is going to be doing is just a helper function to append an error to our errors list. So peak error will take self and the token type. That won't return anything. It's just going to append to our errors an f string, and we'll type expected next token to be this token type. Instead, we got the self.peakToken.type instead. So I'll go ahead and just save time and paste this in here. This is the no prefix parse function error. We'll use this when we're checking the prefix parse functions in a later method. And the last two things that we have to implement, I will just copy and paste these just for the sake of time. It's for checking our precedences. So we have our current precedence and our peak precedence. This just gets whatever precedence level is associated with our current token and our peak token as well. And it will return back the lowest precedence by default if one is not implemented yet. So alright, we can collapse this code block, move down, and we're going to start off with our main execution point of the parser, which is going to be our parse program function. Self and none. Now we will put a pass in here because there's something else we need to set up. We need to set up all of our classes and nodes for our AST. So we'll go ahead and knock that out with one full swoop for just the ones that we need for this arithmetic language. So we'll grab a new file, ast.py. Only a couple imports from ABC. Import capital ABC and abstract method. This is just, we're going to use abstract classes to help with the IntelliSense. So these are some things we need to import for that. And we're also going to have another enum. So from enum, import enum. First class we're going to make is the node type class. This is the type of AST node. This will be an enum. We're going to have the program node, which is like our main root node of the AST, the top most level. We're going to have all our statements right here. The only one we're going to create today is called an expression statement. We're going to have a set for expressions, infix expression equals infix expression, and then we'll have two literals. We'll have our integer literal and then we'll have our float literal. And that should be all the AST nodes we need today. We'll start off with our parent class, so our node. We'll inherit from ABC. So the first thing is going to be, we use the abstract method decorator. It's going to be the node's type. And that will return back a node type. And we'll just pass for now since we're in the parent method. We'll have another abstract method, and this will be for turning the returning back the JSON representation of our node. This is purely for debugging. There's no other reason to have this other than just being able to see our AST in a pretty JSON file. So we'll add a pass right there. So we're going to add two more child classes to node. They're just going to serve as IntelliSense. So class statement will inherit from node and just pass out of that. And then class expression will inherit from node as well, pass out of that. Alright, so let's get on to our first actual AST node. This will be our program node. It'll inherit from node. This will take an init method. Won't take any variables in, but it will have a property of statements. This is just a list of statement nodes. These are just all the statements that make up the entire program that we were creating. We'll implement the type method. And this will just be the node type.program. We'll implement the JSON method. So return a dictionary. We'll have one key for type, and we'll call our type function, you need to use the dot value because node type is an enum, and we want this string value instead of the actual enum value. Next thing, we're going to have a block for our statements. Now we're going to use a little Pythonic thing called list comprehension for this. Just going to make it easy one-liner. You could do a for loop up here and then populate a variable into here, but I just feel like that's too much. We're using Python. Let's roll. So in this list, we need to do for statement in self.statements. And in front of this for loop, we'll make a dictionary. The key will be a statement dot or type function dot value is equal to statement dot, we'll call whatever that statement's JSON value is. And this is going to pretty much recursively build out the JSON AST file, or the AST JSON file. All right, we'll move on to our statements. So we'll make another region block, statements. And we'll do end region. The class will be an expression statement. So we'll inherit from the statement class, which is inheriting from node. This will have an init method. The only thing this will take in is the expression. And then this will default to none. Self.expression equals expression. I guess we'll add a type hint as well. Why not? We'll implement the type function. Node type dot expression statement and the JSON function. Type key will be self.type.value. The expression key will be the self.expression.json. So whatever this expression node ends up being, we want to grab its JSON representation. Alright, we have 3 more nodes to implement. The next one is going to have its own region block for expressions. This will be the infix expression. We'll inherit from expression. So in this init method, this is has a little more going on with it. We're going to have a left node, which of course will be an expression. The operator, which will be a string, and then the right node is also an expression. We'll default that one to none. So this is like the 5 plus 5. Left node would be this 5 integer. Operator would be plus. The right node would be this 5 integer. So in this method, I'll paste this just to save a little time typing it. So just setting these variables up into the class. So we'll implement the type method. So this will be the node type.infix. We'll implement the JSON method. We'll have a type self.type.value. The left node will be the self.leftNode whatever their JSON representation is. Operator, self.operator. Then the right node, self.rightNode.json. Alright, so 2 more. I am going to just paste in here just for time's sake, of course. So we'll have another region block, literals. We have an integer literal. All that's taking in is an integer value and setting up the same way every other node is being set up. Float is exactly the same as integer, except everywhere it says int, you want to grab a float. Now that we have this AST fully set up, we'll save that file and we can get out of that for now. Go back to our parser file. Go up to the top. And we will start importing from our AST. So I have just them segmented out, so like our root IntelliSense nodes pretty much at the top with our program. I'm going to have all the statements on this line, all the expressions on this line, and all the literals on this line. There will be a lot of nodes to import, so I'm just going to go ahead and organize it as I can. We're going down to parse program. Go ahead and implement this function. So first off, we're going to need our program node. Create an instance of that. So while the self.currentToken.type is not equal the token type of end of file, so it's not our very end of the tokens, we still want to parse. We're going to get a statement, and that will bring us to our first function, parse statement. We'll implement that in a second. If statement is not none, we're going to append this statement to our program nodes statements, and then we're going to increment to the next token. At the very end of this, we'll return the program. Return program. We'll return the program back out to main, and that's what will be sent into our compiler. So the next two functions we're going to implement, we're going to put them inside another region block just to help it out. Oh my goodness, I can't spell. Statement methods. There we go. And region. So first off, we have the def parse statement method self, and this will return back a statement. And then this will, as of right now, this will have a lot more in this function, but for right now with our arithmetic language, we don't really need to do anything in here. So we'll just go ahead and parse down to our parse expression statement. Now in our parse expression statement function, we'll go ahead and just copy paste that. That's going to return back an expression statement node. First, we'll set a variable for our expression. So we'll call another function. This is pretty much the root of the Pratt parser, which is the parse expression function. And this will take in the precedence type. We'll just give it the lowest to start off with, because we're not exactly sure yet which precedence we should be giving. And then we'll grab a if statement, so self.peak token is, and we'll check for a semicolon. So that if this statement is done, so in our parser, if we see a semicolon, that means this expression statement's done. We'll just move on to the next token. And we'll build out our expression statement class for AST node. Our expression is equal to expression, and we'll return back the statement. Now, back into the tree, we can get out of the statement methods. We're going to take this parse expression and head on down to another region, expression methods, and region. So we'll do a def parse expression self, and this will take in a precedence, which is just the precedence type, and we'll go return back an expression from that. So this is where we're going to use our prefix and infix functions, parse functions. So we'll go ahead and set these up and give her these comments. So in our prefix functions, we need to just handle integers, floats, and left parentheses. So these are going to call another group of functions that'll parse an int literal, a float literal, and a left parentheses, which is just a grouped expression. There will be a lot more in here, but this is all we need now. And the same with the infix parse functions. We'll paste all of these in, and this is where we'll implement all of our operators. So every single one of these just calls this parse infix expression. So we can go ahead and implement these four different functions these two are pretty much the same. So we'll go ahead and implement these. We'll go with parse infix expression first. So we'll pass out of that and come back to it. So def parse infix expression will be a self. And this will take in a left node, which we'll see in a minute where that comes into play. This will return an expression. The infix expression, build out that class. The left node is left node, and the operator is a self.currentToken.literal. Now we'll leave this right here because I feel like maybe this needs to be explained a little more on how it's called. So we'll go back to the parse expression function, and we will implement this whole function before implementing the rest that need to be called. So the first thing in the parse expression function is prefix function. It's a type of callable, or it could be null or none. We're going to check our prefix parse functions dictionary with the get method. And we're just going to get the self, whatever our current token's type is. We're going to get that prefix function for our whatever current token we're currently on. If that prefix function is none, this is where our no prefix parse function error comes into play, and we'll send in that current token type. Return none. Now we'll grab the left expression, and we'll set that to what our calling of the prefix function that we got up before. Now we need to check for infix operators, or if there's any infix functions for this. So while not, self.peak token is token type dot semicolon, and the precedence value, so we need to use dot value because of the enum, we need to get that integer out, is less than the self dot peak precedence dot value. So while all of that is true, we're going to grab and see if we can get an infix function out of this token, out of the peak token. Self.infix parse functions.get self.peakToken.type. If the infix function is none, we're going to return that left expression. Go ahead and increment to the next token, and we'll set the left expression equal to whatever the result of this infix function. We'll put in our left expression or our left node that we were talking about earlier. In the very end of this, we'll return back whatever the left expression ends up being. So we'll go right back into our infix function, since now we see where it's called from. So we need to get a variable for our precedence, just to save it, and this will be whatever our current precedence is using our function. We'll increment the token. We'll set the infix expressions right node equal to whatever we'll parse that. It is equal to an expression, so we're going to parse the expression at whatever precedence we saved up here. And we'll return back the infix expression. Now we'll move on to the grouped expression. So we'll grab this. This is for our prefix functions. So def parse grouped expression takes in nothing other than self, and we'll return an expression. First thing off, we'll go ahead and increment to the next token immediately. We'll grab the expression from our parse expression method, and the precedence type will be the lowest because we're not sure what we need. If not, self dot underscore underscore expect peak token type dot right parentheses. Since this is a grouped expression, so it's whatever is within two parentheses. So if after we parse that entire expression, if the last one is not a parentheses, that means we have a syntax error. So we'll just return none out of that. The expect peak function will already append that error, so we don't need to do it here. and we can return whatever expression is out of that. Now the last two functions that we need to implement are the parse int literal and the parse float literal. So we'll make a region for these prefix methods and region. Now I'm going to paste these in here and just go over them really quick just for the sake of time. So the integer literal just creates a new integer literal node. We try to convert this value into, or we try to convert this literal into a integer. If that doesn't work, we'll append an error and return none. If it does work, we'll return back that integer literal. And the float literal does the exact same thing, except we're using floats and instead of ints, of course. But all right, I think this parser might be ready to test. I don't see anything that I am missing, so we will go and save this file. We'll go to main.py, from parser, import parser. We'll grab from our AST, we'll import our program, and then we'll also import JSON for our AST. And we'll set another parser debug flag. That'll be a bool. We'll set that to true. We'll go ahead and toggle off the lexer for now. Down here under this if statement, we'll get a instance of our lexer. Source equals code. Nice. P for parser, instance of our parser. The only variable we need to put into that is our lexer. So we'll put that lexer instance in there. We'll set our flag parser debug. I have this little print statement we can add here. I'll also add it up to the lexer just for fun. But in here we're going to need to grab a program node from the parser. So p.parseProgram. We'll open up a file. Before we do that, let's grab a folder, name it debug. And then we'll do debug/ast.json in write mode. Name it f. JSON.dump program.json. That's that JSON file or that JSON method that we implemented for each node. Put f, and then we'll set an indent of 4 just to make it easily readable. And then we'll just add another little print statement down here just to show that this was successful. And now with a little crossing of the fingers, I think we can check to see if this works. So Python main.py. Said it wrote. Here we are, and beautiful. All right, so here's our program node. Every statement in this file right here. So our first statement is 5 + 5, so that's an expression statement. The expression is an infix expression, and that is where left node is 5, the operator's plus, and the right node is 5. So now if we put these in parentheses and we multiply it by 10, according to PEMDAS, multiplying should be this parentheses should be resolved first before we multiply, so we can see how that looks on the AST. So as we run this, now we have a expression statement where the expression is an infix expression. The left node should be another infix expression. That is the 5 for the left node plus 5. And then the right node of this whole expression is just the integer literal 10 with the multiply. So it will resolve all of this first, 5 + 5, and then it will resolve this left node's value times that right node's value. So we have PEMDAS working pretty good now. And we have our AST being built and shown in a JSON file. Now the next thing that we'll work on for the compiler is taking in this AST and walking the AST to generate the IR code for LLVM using LLVM Lite. So we'll get that set up in the next episode. Thank you for watching. If you want to join our Discord, the link is in the description below. If you have any suggestions on features or stuff that you want to see, please do let me know in the Discord. Please do leave a comment, and we will get to that. So I will see you guys in episode 3.